In this part of the course, we're going to focus on how, after we have come up with the entity relationship diagram, how do we actually move this forward to become database tables? And so we're going to talk about a little bit more about ER modeling, things that we need to make sure that we avoid. Then we're going to talk about something called functional dependencies, and finally normalization. So we talked before about a good relational design, that it has to make sure that it captures all the necessary attributes. So all the attributes that the user wants to save, we need to make sure that we save them. We need to make sure that we capture all the relationships that exist, and we need to identify whether they're one-to-one, one-to-many, or many-to-many. Now, we also want to make sure that we avoid redundancy. We don't want to store the data multiple times. And when we avoid redundancy, we are going to avoid having extra storage. So we want to be able to store our data in the minimal amount of storage needed, and avoid having redundant data. We said before that if we have redundant data, that means we have to update the data in multiple places, and that's something that we want to try to avoid. So these are key concepts that we need to keep in mind when we want to create a good relational database design. Now, redundancy, we're going to focus on redundancy a little bit because this is, it's undesirable. It causes several problems. So the problems that are caused, we call those anomalies. And an anomaly means something that deviates from what is standard, normal, or expected. So anomaly is something that's not good, something that gives you a result that we don't want, and we want to avoid these anomalies. So we're going to see some anomalies that exist in databases that have bad design, and then we're going to talk about how do we move these designs to be better. Now, just so we are clear, redundancy does sometimes have an advantage. Think about a pen. If you have a lot of pens, keeping all your pens on the desk is a good thing. It avoids the clutter. But having a pen in every room, on every table, and in the kitchen, and in the garage helps you so that when you need a pen, you don't have to go run to one place and get it. You can find it anywhere. So redundancy sometimes is good. It leads to performance improvements. Instead of running up to the room that has the desk and all the pens, you can just grab a pen from the kitchen table. So redundancy is something that we do want to avoid, but we want to keep in the back of our minds that, sometimes redundancy is a good thing because it helps with performance. But we are going to kind of put that aside right now. And in the next part of this course, when we talk about more SQL, advanced SQL, we're going to talk about how to use join to get data from multiple tables. And in that case, we'll see how redundancy does, sometimes help with performance. But we do want to avoid redundancy. Now, we said that there are multiple anomalies that can occur from a bad design. So one of the designs, one of the bad anomalies that can happen is called an insertion anomaly. And an insertion anomaly happens or occurs when you are inserting data, and it happens when you're inserting inconsistent data. So let's look at this table here. We have a few employees. They have IDs. Each employee works in a department. They have a certain salary, and they've taken some course, and they've completed it at a certain time. Now, we have here redundant data being stored. For example, employee Miki with ID 1, who's a software engineer and has a salary of $8,000. Every time they take a course, we are adding a new line for them, and we are saving again the employee ID, the department, and salary. This is redundant data that we are storing every time we add a course for this person. Now, an insertion anomaly would happen if I try to insert, for example, a third course that Miki took, and I, by mistake, give them the wrong ID, or I put their department wrong, or I give them the wrong salary. In that case, I will have Miki with 2 departments or 2 different salaries, and I will not know which one is the correct one. So that would be called an insertion anomaly. An insertion anomaly is when I try to insert data and by mistake, I insert inconsistent information and now I don't know which data is correct. Okay. There's also an update anomaly. An update anomaly occurs if I have existing information and I want to update it and I update it incorrectly. So for example, let's say Miki decides to change the department that he is working for, or he gets a raise. Now, how many rows in this table do I have to update? I have to update more than one row. If I forget to update one of the rows, I will get an update anomaly. So an update anomaly happens when you go to update the data in your table and you update it wrong, or you update part of it and you don't update all the rows, and then you end up with inconsistent data. Another type of data of anomalies is called a deletion anomaly. Let's look at this table in front of us. Here we have the name of a person, the ID, their major, the course that they are taking, and a course description. Now here, what we are assuming is that the course information is stored only in this data. So I'm assuming that, the fact that CSE 421 is operating systems is only stored in this table. Let's say student Mayor decides to, graduated or decided to leave the college, and I need to delete their entry from this table. And let's say they were the last person taking, in the computer science department. Now, if I delete this row, I have just deleted the fact that CSE 421 is called operating systems. This would be a deletion anomaly, where when you delete a record, you are actually deleting more information than you intended to delete. Now, of course, this is a really bad design, but this would be a deletion anomaly. If you try to delete a row and by mistake that deletes information about something else because you just deleted the last row. So anomalies are what we want to try to avoid. So let's do some practice. I want you to pause this video and kind of answer the questions on your own, and then unpause the video and see if you got the right answer. So here we have a table that has an employee ID, the budget for a project they are working on, the project that they are working on, and the number of hours that they're working on the project. Let's look at what would happen if I try to add employee 85 with a budget of 35 for project 1, and I say that project 1 needs 9 hours. What would happen if I add a row like this? Well, the first thing to notice is that employee 85 doesn't exist, so adding a row like that is okay. Now here from this table, if I look at it, P1, project 1 has a budget of 32 hours. Project 1 has a budget of 32 hours. Project 2 has a budget of 40. Project 2 has a budget of 40, and project 3 has a budget of 27. So the budget and product ID columns in this table, they are tied together. So the budget is related to the project, and then here it lists, how many hours this employee is working on each project. So if I come up in here and try to insert another employee to work on project 1, and by mistake say that project 1 has 35 for its budget, I'm going to be changing P1. So P1 has 32, and now I'm going to insert another row that says P1 has a budget of 35. That's going to leave my table in an inconsistent state. This would be an insertion anomaly. I'm inserting data that causes my table to become inconsistent. Basically, project 1 now is going to have an inconsistent budget. Now, what happens if I decide to delete the row S79 over here, with a budget of 27 for project 3 and hours 1? If I delete this row, this employee stopped working on the project, I'm deleting them, but by mistake, what I'm also deleting is everything related to P3 here, which is that P3 had a budget of 27. And so if I delete this row, I will end up with a deletion anomaly because I am losing more information than I intended to. I am losing now how many hours, what's the budget for project P3. So that would be a deletion anomaly. Now, if I go to update S75, who's working on project 1 for 7 hours, I go and by mistake changed it so that P1 has a budget of 35. Again, I am messing up the budget of project 1. This will be an update anomaly. Now I have P1 having a budget of 35 somewhere and P1 having a budget of 32 somewhere. That is bad because now I have inconsistent data in my table. So because this table contained redundant information, it contained the budget corresponding to the project in more than one place, I would be getting an insertion anomaly and an update anomaly. Now, because here I am storing the same in the same table information related to a project, its budget, I'm storing that in the same table that I'm assigning employees to projects and saying how many hours they are, because I'm kind of storing more than one entity information like this, the project information should be in one table and the employee information should be in another table. We should have an entity, a table for employee stuff information, and we should have a table just for the project information. But because I by mistake combine these into the same table, if I delete the last employee working on a project, I am deleting the project itself. And so I would get a deletion anomaly. So these are anomalies that we want to try to avoid. And the way we're going to avoid them is by something called normalization. And normalization is what we're going to learn to do in another class, part of this part of the course. But if I wanted to, quickly do it, I would basically say project information needs to be in one table and employee information needs to be in another table. Okay, so how to avoid anomalies is what we are going to be discussing. Now, before we jump into how to avoid these anomalies, we need to learn some concepts. So a functional dependency is a relationship between two attributes. Typically, it's between the primary key and another non-primary key attribute within a table. It occurs when a candidate key determines all the other attributes in a table. What does that mean? A functional dependency happens when you have some attribute, and a functional dependency already exists between the primary key and all the other tables. So when you're choosing a primary key for your table, you are choosing a unique key that will uniquely identify every row in your table. So let's think of a social security number. If I'm storing information about a person, the unique way of identifying a person living in the United States is by their social security number. The unique way of identifying a student at our college, is by the banner ID. The unique way of identifying a book is by the ISBN number. So we say that here, if I have SSN, determining name, address, and birth date, we say that name, address, and birth date functionally depend on the social security number. They are dependent on attribute X. So if I say X arrow Y, I am saying that attribute Y is functionally dependent on X. If you tell me X, I will be able to tell you Y. If you tell me X, I will be able to tell you everything because X uniquely identifies Y. Another example is if I have two composite, here I have a composite key. If you tell me a course number at our college and the section number, I will be able to tell you who the professor who is teaching it is. We say that X is the determinant because it is the one that's determining everything else, that you can find everything else from. Y is the dependent. It depends on X. So the title of the book depends on what the ISBN is. Basically, if someone tells you X, then you'll be able to determine Y. So if someone tells you the ISBN, you'll be able to determine the title, the author. If someone tells you the social security number, you'll be able to determine their birth date. So here, a functional dependency exists between two attributes, and it exists between two attributes where one of them is the primary key, or it could also be a candidate key. So let's review the definition of a candidate key. Candidate key is a key that could have potentially been be the primary key. Now, it's one that I decided not to choose as the primary key. And so, again, if attribute Y is functionally dependent on attribute X, then attribute X is a candidate key. It uniquely identifies a row in that table. Now, let's look at this table here. And I want you to look at it and tell me which attributes are candidate keys, and I could be able to use them as primary keys. So here I have the name of a couple of universities, I have their address, I have which state they're in, I have the enrollment, how many students are enrolled in them, and I have the population of the state that they are in. So I have two universities here, for example, in Connecticut. And so because they're in the same Connecticut, the state population for them is the same. Now, if I gave you this data and I told you I want you to determine what keys are candidate keys, what would you say? So we find that there are several columns that would be candidate keys. So the university name, that could be a candidate key. I could make the university name the primary key, or I could use the address because the address is unique. You only have one college or one university at a specific address. So the address could have been the candidate key. Or I could have said, well, I want it to be the address and the state. That is also a candidate key. It's not minimal, but the address and the state that it's in, that could be the candidate key. So here I have several columns or several attributes that could be candidate keys, and I am free to choose which one I would want to become the primary key. Now, when I identify my primary key or my candidate keys, I can get from that those functional dependencies. So if I decide to say the university name is going to be my primary key, then I know that the university name determines the address, because if you give me the university name, I can tell you what the address is, I can tell you what state it's in, and I can tell you the student population. I could also tell you the state population. So basically, the primary key when we're looking at functional dependencies, X, if Y depends on X, functionally depends on X, X is going to be a primary key. And so here, because the university is a primary key, it's going to be able to determine everything. Now, if I wanted, so here what we could do also, instead of like just listing them individually, we could say that the university name will determine the address, the state, and the state population, and of course the enrollment, which is missing here. But here I have a functional dependency. And when you are analyzing your tables and you list those functional dependencies, it helps you identify which column could be your primary key. So if you're confused about which column to choose as your primary key, listing those functional dependencies help you determine which column should be the primary key. Now here I could have also said that the address and state determine everything else. So if you tell me the address and the state that it's in, I could tell you the name of the university, I could tell you the student population, and because here we have the state, I could also tell you the, the state population, the enrollment is there, but because we have the state, I can tell you the student population, the state population, sorry, this should say state population. Okay, now let's see if we had picked the wrong column for our primary key. So let's say someone, says, I think the state is the primary key because the state determines the state population. So this observation is correct. If you tell me the state, I can tell you the state population. So Massachusetts is 6.9, Connecticut 3.5, Tennessee is 6.9. So the state determines the state population is correct. So we can say that there is a functional dependency between state and state population. Now, if we wanted to go and say the opposite, if I say population determines the state, here we have two states, for example, Massachusetts and Tennessee with the same state population. So the opposite will not work because I have two states that have the same state population. So if you tell me the state population, I'm not going to be able to tell you which state it is. So this would not be a functional dependency. But looking back at state determining state population, this is a true functional dependency, but it's only a functional dependency between the state column and the state population column. It's not telling me the other columns. So this would tell me that, yes, I know there is a functional dependency between these two columns, but I cannot determine that state is the primary key because state does not determine everything else. Okay. Now, if you wanted to go into more details, you can also see that the value country, the country is always USA here. So our data is always USA for the country. So we could do a generalization. Say, if you tell me the university, I can tell you the country. If you tell me the address, I can tell you the country. If you tell me the state, I can tell you the country. If you tell me the enrollment, I can tell you the country. If you tell me anything, I can tell you the country. But this is only true because all our data has the same country. So again, although everything here determines the country, it's not really a true functional dependency.